Last time, I walked you through what really happens when I press the power button on my computer. But today, I want to take you deeper. Because while the screen is still loading, two components are already working very hard behind the scenes: the CPU and the RAM. Today, I'll explain what they do, step by step, in a way that makes sense whether you're a beginner, an office worker, or an ICT professional. In the previous lesson, we saw how the operating system loads after BIOS and the bootloader finish their work. But the operating system does not load by magic. It needs two things: a processor to execute instructions and memory to hold data. That's where the CPU and RAM come in. As soon as power flows and the system passes its initial hardware checks, the CPU becomes active. The CPU, Central Processing Unit, is responsible for executing instructions. In simple terms, this is where thinking happens. Every instruction, from checking hardware to loading the operating system, is executed by the CPU. Technically speaking, the CPU begins executing firmware instructions and later kernel instructions using the fetch, decode, execute cycle. If that sounds complex, here's the simple idea: the CPU reads instructions, understands them, and acts on them. While the CPU is busy executing instructions, RAM is doing something just as important. RAM, Random Access Memory, provides temporary working space for the operating system. When the operating system loads, it does not run directly from the hard disk. It is copied into RAM. Why? Because RAM is much faster than storage. I like to think of RAM as a work desk. The bigger the desk, the more work you can spread out comfortably. From a technical perspective, system files, drivers, and kernel components are mapped into memory during boot. Here's where the real teamwork happens. The CPU cannot work without instructions and memory. And RAM is useless without the CPU to process what's inside it. During startup, the CPU requests instructions, RAM delivers them, the CPU executes them, results are stored back in RAM. This happens millions of times per second. That's why CPU speed and RAM capacity both affect startup time. In an office environment, I've seen two computers starting at the same time. One boots quickly. The other takes forever. The difference? One had enough RAM. The other didn't. The CPU was ready to work, but there was not enough memory to load everything smoothly. That's not a software problem. That's a resource limitation. When RAM is insufficient during startup, the system starts using storage as virtual memory. This process is called paging or swapping. Technically, it means the system is borrowing space from the hard disk to act like RAM. But storage is much slower. So the result is slow startup, freezing delays. This is why adding RAM often improves performance more than upgrading the CPU alone. Many people believe that a faster CPU automatically means a faster computer. That's not always true. A powerful CPU with insufficient RAM will still struggle. Balance matters. The CPU thinks. RAM remembers. They must work together. If I open Task Manager after startup, I can see how much RAM is already in use. Even before opening any application. That's the operating system occupying memory so it can function properly. This shows that RAM is essential even before user activity begins. So let's summarize what happens during startup. The CPU wakes up and begins executing instructions. RAM provides fast working space for the operating system. System files are loaded into memory. CPU and RAM work together continuously. Startup speed depends on both processor efficiency and available memory, so the next time your computer starts slowly, don't just blame the software. Look at the CPU. Look at the RAM. And understand the relationship between them. I'm Hannah, and this is ICT Made Practical.